Hello, Sam.
Hi, Hassan.
Waiting for, oh, Alan's coming in. Good morning, Alan. Let me just text Professor Choniek. Hold on. Oh, he's here. Good. Good morning.
Good morning.
Well, we could start. I would like just to really gratefully thank the committee members, Professor Choniek Tang and Samuel Chung, for agreeing to, do the defense on a Saturday. I know it's a weekend, but given the circumstances that Fifi, received the job offer and he's starting soon, and he left really town to San Diego early this week. So that really pushed us to do it before he starts his job in San Diego. So with that, Afifi joined me in summer of 2019. He worked on multiple really ODOT projects, things that he did, but he was mainly the lead on the RWIS, the Road Weather Information System that developed for the ITS group. And I see Mr. Alan Stevenson is on the call, and Alan was the instrumental in really funding this project to deploy the system that Afifi is going to talk about in a few seconds, and the data that were collected for that. So Afifi, please go ahead and start your presentation. Let me just make you a co-host so you can share your documentation. Afifi, we can't hear you. Just make sure you're not muted.
Hello, everyone. This is Mohamed Afifi. First, again, I would like to thank the committee for agreeing to attend my defense in a weekend. I would like to express my special appreciation and thanks to my advisor, Dr. Afify, for monitoring and encouraging my research work. I would like to thank the committee again, Dr. Cheng and Dr. Tang, for serving as committee members for me. My thesis defense today will be discussing the RWIS-based road condition prediction using machine learning algorithms. First, I will be starting with a quick outline of what I'm going to be talking today. First, I'm going to be giving a background about the system and why it's important, a quick introduction about how it's working and how it's related to our work area. Then I'm going to be giving a quick objective about what is my thesis actually doing step by step and what I'm going to be walking you through in my defense. And I will be talking about the related work done in the same research field. I'll be talking about the RWIS system, what is it, what is the type of data collected, and how it's getting reprocessed to have a clean data set. I will be talking about the importance of the GFS model, which stands for the Global Forecast System. And I'll be talking about the EDA, which is explanatory data analysis for the data set collected. And I'm going to be talking about two branches of models, which is the regression and classification. and how if each model needs a specific type of dataset preparation. And I'm going to conclude the work and show you my references. For the background, winter events in Oklahoma are very severe due to the cold fronts that affect the state during the period of winter. Most of the time, these events are not really predictable and can predict really worsened conditions that is expected to have a huge of the temperature variations. According to the US DOT, on average of 10 years, we have around 156K of crashes and 521 fatalities during that period. And despite there's severe weather like the tornadoes, still ice fatalities are much, much higher than the tornado one. Forecasting the surface temperature and the conditions of the road can decrease the impact of accidents and help the state government to do better work on the road treatment. The picture here is from February 2021 blizzard that affected Oklahoma and Texas, where 133 cars piled up on the I-35 near Fort Worth, Dallas, and it's somehow near to one of our stations I'm going to be discussing later on in one of the slides. Another background, what is a cold front, how it's affecting and why it's important to study this part. The cold fronts that affect Oklahoma State can really have a severe sharp drop during the autumn and winter season. Strong cold fronts can make really sharp drops in the temperature, and that type of cold fronts are called ammonia fronts. That's how it's stated by the meteorologists. And as shown in the figure here, if we look at the northwest side, we can see the temperature are below the freezing level, while the other part of Oklahoma State is actually having a summer temperature. This sudden drops doesn't affect the surface of the roads and the bridges. In the third picture here, the black color is the ambient temperature with the air temperature, while the blue and red is the bridge surface temperature and road surface temperature. And we can see here the surface and road doesn't really get affected by the below freezing level air temperature, and they become above the freezing level. And that actually becomes because of the heat radiation that affects the surfaces, especially in the autumn season. Last thing, most of the cold fronts that affect Oklahoma doesn't contain any wintry precipitation, even with a freezing level, and that chart proves what I'm saying. As the sun radiation causes a release of heat energy into the atmosphere, as shown in the third picture, and the warm mass on the surface start to rise up the cold front, and we have a really warm temperature on the upper surfaces, and that will be explained in a further slide. This is my objective that I'm going to be discussing today in my thesis defense, and I'm going to be showing the work done related to what I have done in that study. I will be describing the system used to collect the data used in the thesis, its location and what is the data features I'm going to be using, discuss the methodology used to prepare the data for modeling, demonstrates the importance of GFS model and why it's important to add to the scheme of the process. And finally, I'll be training my models and show which one has the best performance to predict the temperature surface and the condition of the road as well. For the related work, the meteorology part doesn't have much research paper to predict surface temperature, especially using the new machine learning techniques. And most of the research is actually based on heat transfer physics models that used in the late 90s by the meteorologists. I found 3 papers that have covered the same topic. One of them has machine learning and one of them has a statistical study done by United States. First one is using one-dimensional heat balance, which is based on solving heat energy by calculating the heat flux. Due to the heat flow of the phase shift to freezing and melting of snow, the model is predicting the road surface temperature using a mobile station that collects the normal data temperature, humidity, wind, precipitation. And they got 4 types of metrics. The best of them is 1.89. but the model is more of localized and globally used. So they cannot using in another segment, and it must be used on their road due to some coefficients that they added to the model to make it more localized to their predictions. Second paper is using a machine learning model. It's added by the Peking Meteorological Service Center. They used a lot of metrics as accuracy on RMSC, and they got around 3 Fahrenheit. They used an ELM, which is an extreme machine learning model with an activation function of a soft plus. They got, as I said, accuracy of 81% and 3 degrees, and that's what are they using. Third one is a statistical paper that added by United States NOAA. It's based on a statistical study on a relation between the surface road temperature and the number of accidents that occur. And according to their study, when the surface temperature crosses the freezing line, as shown in the blue line, and recross it again, that causes the melting of snow and refreezing it, which making the most hazardous condition and the most number of accidents occur in that incident. Second, I'll be talking about the RWIS system. We have 15 stations deployed by ODOT, and it were programmed by the help of Dr. Afify research team. The stations are along 209 miles, starting from K County to Love County in the south. It measures real-time data that collects 36 features. I'm using 16 features of them. I will be talking about what are the 16 features here. This is how the RWIS station looks like. We have 2 IR sensors, 1 camera, and a climate, and 2 subsurface temperatures. What are the data collected? So this is climate, and this is what I'm using in my data set. So that is climate is collecting temperature, wind speed, direction, gust wind speed and direction, air pressure, precipitation event intensity, what is the total and what is the time of that precipitation, and what is the brightness level and the air temperature. The IR is collected the road surface, and the other one is collected the bridge. Dew point is an important factor that I'm using here, as it will tell us what is the maximum temperature on the day after, and it's going to be useful for the dataset to locate some of the points. 2 subsurface, one is 2 inches below and one is 6 inches below the subsurface. For the data pre-processing, I use 6 stations highlighted in the green color, 2 in the north, 1 in the middle, and 3 in the south. Some other stations at that point of procedure, it had some faulty sensors and some power issues. Data were collected at different rates. I collected the data, so I resampled the data at 5 minutes, 15 minutes, and 1 hour to satisfy the time series conditions so the model doesn't get mixed up. Each attribute is processed through a query function. That function will remove any outliers, NaN values, and if I don't have data for 15 minutes, I will dismiss 12 hours. If it's more, I'm going to dismiss the whole day. IR had a special pre-processing. I will be discussing how to get pre-processed in the second slide. I created an API RESTful function. The function will help the user to just plug in the station number, what is the date from to, what is the sample size of the time series of data, so it gets resampled, and it will just return a database to the user that he can immediately use it in any model he wants, and it will be cleaned and pre-processed. For the IR sensor, IR sensors are so sensitive to the outdoor atmosphere, and it can record a lot of misleading data due to the reflective surfaces. As a vehicle travels on the road while passing through the IR angle of reading, there will be sharp drops in the chart. To remove that, it will simply remove the outliers, and it starts to look like a good temperature reading, but still have some spikes that the model will predict spikes in the target. And that's why I used a Gaussian filter with a 1D. It's a standard deviation of 10 pixels. And that's how it looked after filtering the IR sensor data, look clean for modeling section. In that section, I'll be discussing what are the different types of precipitation and how we can detect that type of precipitation from the chart. Not all winter precipitation are really dangerous, as snow doesn't make the road dangerous for vehicles, except under some conditions where the surface can melt and refreeze again, as I discussed in the related works. The upper atmosphere level is between 500 and 800, where usually all the time of precipitation occur. Unfortunately, our station is way below that levels and cannot detect what's happening in the upper levels. And at some times we can have an air temperature under the freezing level, and still we can see rain precipitation. This is based on the temperature in the upper atmosphere where the precipitation forms. That can be detected from the SQT diagrams here. Basically, that's how the meteorologists use it to detect what is happening in the next 12 hours. In that graph, this is SQT, we can see the diagonal lines are the temperature values. This is a millibar pressure, and this is actually what is how many feet are we above the ground level. The green line is the dew point, the blue one is the red one is the temperature. When the green and red start to separate, that's when the cloud formation starts, and when they diverge, that's when the clouds stop forming. So based on that, where did that it formed? So we can see here the diagonal line of the surface, so we can see a below freezing level at the surface point, but above that we can see it start to coming warm again and above the freezing level. And that kind of condition start to form sleet kind of precipitation. This one is more simple to show you what type of winter precipitation we can detect. First one is freezing rain, and when it starts to skew above the freezing level by 3 kilometers. Sleet when it starts to skew for 1 kilometer, and rain when it's all above the freezing level, and snow all below the freezing level. For that condition, I said RWIS can only locate the surface layer and won't be able to read any other information. Also, if there is a cold front storm formed and it's about to enter the state, RWIS dataset won't have much information, and the forecasting accuracy won't be that great. The most used powerful model in the meteorology is the GFS, which is Star State for Global Forecast System. NWS, which is National Weather Services in the US, has another localized one of the GFS called HRRR, which is High Resolution Rapid Refresh. It updates the model every 1 hour. The normal one updates every 6 hours. Performance in 24 hours is really high. It's always above 90% according to the NWS. As I mentioned, the GFS can track any storm. As we can see here, it's in the February blizzard, there was a storm already catched by the GFS in Colorado, and it was moving towards Oklahoma State. By adding this kind of information to the RO stations, they can really detect that there is a storm approaching, and it can have a better accuracy of tracking the movement and give a better accuracy of what is the temperature is dropping to. So for that, I used an API services called ClimaCell. It can parse for me all that kind of information, like the precipitation type and the temperature of the air itself. In that two graphs, we can actually locate a square area, and the dataset will return what is actually the type of precipitation coming through that, or what is the temperature in that, the mean value of the temperature in it. And I can just add it again to my RWIS dataset and add it as a future value for the model to have better prediction. In that section, it's like an outline of what's happening. I'm going to be giving data analysis and what is the regression models. So I'm developing a regression model to predict 1 hour to 12 hour in a 1 hour period of what, and I'm going to be predicting the road and bridge surface temperature. I'm going to be developing a model using as one single station, and I'm going to develop another model that using ensemble data to have more global system, and I'm going to use a model that using a combination of the ensemble and the GFS dataset. The best accuracy without the GFS achieved was 2.5 RMSE for 12 hours period. For the exploratory data analysis, I will be analyzing the collected data and make an EDA for the data set. The data should be suitable for regression models, so it can see any kind of non-random build in the chart. So I need to see the correlation between each feature and the other, and each feature and itself. The first graph, and on this graph, it shows the bright intensity and how it's correlated when there is kind of winter precipitation. It drops due to the low intensity of light. Second one is the dew point, and this is one of the most important features, because when air mass is before the cold front, it's really high, and when the cold front passes, it drops. And that's how the station can detect there is a cold front actually passing across, and there is maybe a dangerous feature. This graph here shows how before the cold front, the dew points are much higher than the dew point temperature before the cold front, and that's explain why the chart drop when the cold front passes. Third one is a normal temperature distribution. When usually in summer, before the autumn and winter hits, we can see a seasonal waves of high and low with a much big difference. But when the winter events start to hit the state, the high and low doesn't have a noticeable much change. And that how also can be a way for the model to detect it. In that slide, I'll be proving if the dataset is actually good for regression models and if it have a good score matrix for correlation and distribution. And as I said, between each feature and another feature, and second, between the feature and itself. The first graph here is a correlation study between each feature and the other. The correlation is based on a Pearson correlation. And we can see here, for example, we have the target is surface temperature, and we can see for example, when the air pressure drops, the brightness drops too. We can see a big correlation between the all temperature data. We can see between the wind direction and the pressure, and because when the cold front starts to enter, the pressure drops, and also the wind direction is swiped from a southeast to a northeast, and this is like a 360 change. Second one is a EDA study between each feature and the other. I'm only showing here one feature, which is the road surface temperature. And first graph is red is safe, green is dangerous. It shows when the temperature drop, we can have a dangerous class, and then the other graphs is like a trend, seasonal. Does it have a seasonal? Does it have a residual? And the residual is actually the leftover after fitting a line. So it should be around the 0 level, and there is a distribution histogram, box plot, autocorrelation, and partial correlation, and that's proof how it's good for regression models. Second, regression model, the data set we have for regression model is a time series, and I need to convert it to a supervised learning data set. So the model can learn the row, and because it cannot learn the column, which have the seasonal shape. So to have the seasonal shape in a row side, all the attribute of sequence were shifted from the historical to current, and the target will have the future from future to a certain point. And I had it sets from 1 hour to 12 hours, as I said, of historical and future. That will show the seasonal shape inside the row, and the model can detect it well. And the forecast target will have a row of values. Usually we have many features, but all features will be in one row. But the target will only have one feature, which is the surface temperature. The first model we have is a machine learning models. As mentioned, the data are in 5 minutes frequency. I will be training each model 12 times. It will predict 1 hour, 2 hours, until 12 hours. Each model will generate a bunch of RMSE distribution, as shown in that graph, because we have multiple rows of predictions. So we will have RMSE of each row. So I will have a histogram of the distribution of the whole thing. I train 5 models, which is ridge, lasso, kernel ridge, and stochastic gradient. The graph show the performance of 5 models in the second one. X-axis are the number of hours predicted for the model each time. RMSC is the value. As we can see, kernel ridge, the most performance started with around 1 point something, and it ended around 3.4 for 12 hours. We can see here in that graph how the kernel ridge predicted the rise of temperature. This one is for 9 hours, this one is for 12 hours, as it can detect the rise of temperature. And I will be analyzing more models in the second slide. Second slide is talking about the LSTM, which is the neural network part modeling. It's a better version, as we know, from the RNN, and it has good performance for time series data sets. The model have overall the best performance. The architecture here is basically built on trial and error with 3 layers and 1 dropout for preventing the overfitting, and I had an early monitoring function to stop it if it's more than the number of epochs that I added. The loss curve has a very good learning scheme. In second one, I will be showing, this is a 3 hours forecast, 6 hour, 9 hour, and 12 hours. And we can see the RMSC is actually around good values. We can, in the table here, 3 hours had a 1.5. So the 12 hours has a best performance 2.5, and that was the best one I got, as I mentioned in the outline section. That's when there is a drop in the temperature. The LSTM was able to catch the drop really well, and it shows that we can use it in temperature prediction. The models that I just talked about last slides were a local model. It cannot be used on another station. So I needed to make an ensemble model to be used as a global one to predict the whole highway instead of one model to predict each segment. I used a model weighting average ensemble. It usually combines the prediction from multiple neural network to reduce the variance of prediction and reduce the generalization error. On the left side here, it is a model scheme, each model of each station, and it will go to only one neural output. On the right side, this is a table using the normal LSTM, and this is the ensemble LSTM. I used the local model of station 2016 to predict all of them. And we can see station 2013 was really well, and then start to go above the 3. But when I used a global one, it was all around the 1.7 to 1.8 and 1.5 even for all 6 stations. And that proves that this is a really good global one that can be used in everything.
Afify?
Yes.
A quick question.
Yes.
All the RMSC are in unit Fahrenheit, right?
Yes, exactly.
Okay. All right.
And here the ensemble model is used to see if it's good at, so I don't care about anything except the temperature drop and the rise. And as long as the model can predict what is the level of drop and what is the level of rise, this is a good scheme for me to move on with it. Last study, I'm combining the dataset with a GFS model, and I will be adding the forecasted temperature to the model. Here I'm only adding the temperature feature. It actually helps the model to project the sudden drops better and enhance the performance using the current data and the past data. Best model was random forest and polynomial. It had around 1.2 RMSE, and I picked the random forest for further study. For the regression model, this is first graph is for the bridge, second graph was for the road. We can see as long as the data points are along the diagonal, that means we have a really good RMSC. This is my metrics of testing the model. I had a 1.36 RMSE for the road and 1.3 for the bridge. This is some other general metrics core measurements. The last one's accuracy. How I use accuracy for that, I picked 1.5 RMSE as my true value and just added the normal equation. To see if it can predict the sudden drops, I performed it in 2 events. That event is on 6th February. The second one is 21st February. The red line is the predicted and the dashed blue is the real. The black is the air temperature. And we can see how it follows the bridge and it follows the road on both sides really well. Why it's really accurate? Because I'm already feeding it with future data set from the GFS, so it can know when there is a precipitation event or the bridge drop is happening. And that's why it's really accurate. And in my study, I was saying why GFS should be added to the dataset. This is accuracy metrics of the 2 cases, 6th February and 21st February. Basically, the RMSE was high, but the accuracy was really good because the drop was followed exactly the same, but when the rise, it didn't catch it really well. Second one, I'm going to be talking about the classification model side of my thesis defense. The objective is to develop a classification feature so I can detect the road condition, which is hazard or safe, how the dataset got reshaped to have to forecast it for each class value, a correlation analysis to be conducted on some data visualization, developing a classic machine learning model, and second, I will be adding another LSTM classification model, and I will be adding a joint regression LSTM and GFS. It's not a machine learning model, but it's like a statement model. I'll be talking more details on it later. I got an accuracy of 92% for the gradient boosting classifier. I'll be talking about that later on too. So first, based on the information I just gave on how I detect which precipitation event is hazard and which is not, as I said, freezing rain, sleet is more dangerous than snow because it acts like more of sand, it's not slippery. And it can still be dangerous if the surface temperature crossed the freezing level upside and downside in a 12 hours window. The formation of snow can be detected by some meteorological agents like NWS or NOAA, and some even other pictures added from ODOT and provided still by NWS. I collected that information. All information was actually based in Oklahoma County, which is only one station, which is station 235 in Oklahoma City. Data were recorded and added to the dataset. In that graph, it has a lot of features. Let me talk one by one. First, the left side of the y-axis has what is the class value, what is the condition of the road, and on the right side, this is the surface temperature. Below is the date. The red line is the surface temperature, and the yellow line is the precipitation intensity, and any sharp edges we have a precipitation detected. The green one is the dew point, and any drop will detect there is here's a cold front, here's a cold front, here's a cold front, so we can detect cold fronts occurrence too in the graph. The dark blue bars indicate a hazard condition, and we can see it's followed by a drop in the temperature. Some others had drops, but still didn't get really dangerous. First, like the autumn side, it didn't get dangerous because the heat radiation of the road was really high to have any hazard condition. The gray one is actually just rain. The blue light is wintry precipitation, but it's not dangerous. The number of data collected is 36K of a dry and wet. Snow was only 341 event. Sleet, and freezing rain was 4,402. And that can show us we have imbalanced data, and that will be a challenging point for the classification models. And some models will have really high F1, will really have high accuracy, but still F1 accuracy is really bad because that number won't will be, if it's predicted 0 still, we will have a good accuracy. So accuracy won't be a solid measurement in our case. With the classification I mentioned before about the accuracy part and imbalanced data, some changes to the data set should be happening here because after I modeled, I didn't get really good data. So I did some scaling, some transformation, and actually BCT is, I'm doing precipitation change, which is current value minus the previous one, and I will be predicting the drops between each one and the before one, and add the class value to it. First graph here is a covariance ranking algorithm. It computes the mean overall mean value of the deviation of features. It's more generalized as a Pearson correlation, and any side, if it can detect if it's like really have high correlation in temperature side, precipitation with temperature. The second one on the right side, because I have high dimensional features, I need to see if I can see any clusters, and this is a good visualization to see if we have any clustering side. So I can use unsupervised learning machine, but it didn't have much information, and I didn't proceed with that because of the graph shown here. Second one, it's a RWIS visualizer. All features are over the circumference. 0 is the center where all points are normalized. We can see some correlations between the safe is blue, dangerous is green. And we can see the safe tends to be more correlated to the temperature values, and the dangerous is somehow is correlated to the precipitation side. I added a 3D BCA decomposition to see if I can decrease the dimensionality and it can have good clustering side, but it didn't show much information still, and no more future work was added in that section. For the classification part, it's hard to have a time series and forecast a target value. So I had some techniques that I came up with to show how I made some machine learning models out of it. So first, I had a window of data. So I had a window of 72 data rows, which is add up to 6 hours of rows, and each one will have one class value to see if we have that condition that's a target value. And because I'm forecasting, so if I added that the current one, it won't work. So I shifted the classes, so that one will have the future one, and then I crossed the intended one. And for the window side, some machine learning take a 1D input, so I flatten the windows so it can just take one window and one class value. For the machine learning models, I analyzed 3 models with a 6-hour prediction. The 3 are logistic, Gaussian, and gradient boosting. Gradient boosting was the best for performance. As I said, I'm mainly focusing on the F-score, and precision recall was not that great on all of them, but overall, we can say here that is our main target, the dangerous, in the confusion matrix. And as I said, this is a logistic regression. This is a Gaussian naive Bayes, and it's not that great for the dangerous part. And the last one is the gradient boosting, which actually a combination. It's an ensemble of weak models to make a really good one, and it has the best score, which is the dangerous side was really accurate detected with an F1 score of 0.57. Second part, I did an LSTM classification models. It can take high dimensional, and I don't need to have a 1D dimension for the inputs. The architecture of the LSTM model is actually the same, except I added a batch normalization. So because I have here a huge high dimensionality, and I need to fasten the process, So I added the normalization part of it, so it can increase the convergence rate. It will give batches of accuracies. It won't give a final one. So this is a mean accuracy, and this is one that won't relate to that because it's just one sample of many classification side. Second one is I added one more class and I tried to see how it's gonna well detected, and it's 78%. That model is overall has really good performance, but I only here trained 4 hours of forecasting, so it's not that much. Last model is an if-else model. It's a joint between an LSTM surface temperature prediction and GFS model. So basically, here I had the data from RWIS and the API GFS model data. The RWIS will have an LSTM ensemble and it will predict the road surface temperature, and this GFS forecasted. It will have the precipitation only. I'm here parsing the precipitation and add it to the dataset. So if it forecasted below 32 Fahrenheit and we have event one is actually having this codes of precipitation events, which is actually freezing rain, sleet, not snow. If it's snow, it will be still safe because we are in under the 32 Fahrenheit in a 12-hour windows. It will predict the road is safe. Otherwise, it will be dangerous. If both are happening, this code and this code, and the temperature crosses 32 Fahrenheit and the freezing level and went up to melt it and freeze it again, it will be dangerous for both sides. Otherwise, it will be safe. That really that was really accurate, and I did it for 12 hours and I tested in 2 events. The 2 events were a freezing rain in October 27 of 2021 and December 1st. We had some flurries, which is a snow event. And actually it got like 100% accurate for both events. And I did it based on historical data collected from the GFS and our RWIS system. And that is the last classification model added to that study. And that's the end. My conclusion, as I said, best performance was added by the gradient boosting, which is 94 accurate, but still the F-score was a little bit low. And I had a 2.5 RMSE for the regression part. I stated that when we combine the GFS model with our dataset, it will enhance the overall performance, and I show that in each of last section of each one. Real-time training will enhance the model performance in the future. To state that, this is a graph from GFS. They stated the correlation of the forecasting is increasing year by year due to the incoming data sets, and it enhancing the model side. I did that by giving the model data slice by slice, and the data RMSC dropped when the winter entered, and it started to predict well, and it indicates that in a year and a half by ARIMA model that it can really become better and better and reach almost 0 for RMSE. Last, these models can be utilized to solve a lot of issues like traffic accidents by enhancing the road salting procedure if that models are well used in the 12 hours period. And this is my reference, and thank you everyone.
Thank you, Afifi. Good presentation. I'll open the floor really for questions from anyone that would like to ask a question. Abdullah, are you asking question?
Can I ask a question?
Yeah, go ahead. Anybody can ask.
Thank you very much. Okay, very good. Can you please go to the slide?
Sure. It's so as I said, I treat the snow as safe also, but here I added a snow, and so I split it, the slick, which is a hazard, and the snow is safe, into another two classes, and then I start to predict how it's gonna detect the snow, which is I said in the table back in give me a moment. Yes, here I said I have really low number of classes of snow and it's hard to predict, so I just tried it out for the LSTM. That's it.
Fifi, since you're on this graph,
Okay.
so this is the data that you used
Mhm.
to train your classifier.
Yes.
Right? And you said that you collected it from different sources.
Yes.
Did you, I mean, how would you really make sure that the data that you collected from different sources, because you had some from your RWIS, so I understand that you maintain the RWIS, so okay, you know the error or the uncertainty in the data and your data. But if you collected from other agencies, how would you know that this data that you collected to train your classifiers are accurate?
So first there is a historical data set for the pictures of actually the road from some webcams on the winter events. And as you know, like I only working on the winter period of 2021, and I can actually manually go and check the picture by myself. And in the same time, I will go to the NWS office, which have some meteorological and some like the public also can say, okay, we have 12 inches of snow, and they will report the road today is slick, the road today is only wet, and I will start adding classes based on that manually. And I will fill other data with the precipitation type from the RWIS itself, and I will start to see if RWIS can double check with me with the precipitation type is it right or no, and that's why I only added in one station.
Okay. And so when you say local, like you mean like the station localized to the station itself, right?
Yes.
Okay, so it's not local like a region, it's just the station, the segment where the station is located.
Yes.
So here I see that these events, the sleet and freezing rain events, they were 4402 events that reported by National Weather Service and others that these are sleet and freezing events.
Yes.
So if you go to your slide that you talked about, I didn't catch the slide number. I usually copy them, but anyway. So go ahead to the one that shows 87% accuracy.
Okay.
You had a slide that had 87% accuracy.
This
No,
one?
87, the one before it. Yeah.
Okay.
So if you zoom in, where is your hazard? I cannot see these on the confusion metrics. I cannot see.
I added dangerous and safe.
Yeah. So dangerous. You had 874.
Yes.
Right?
Uh-huh.
So you detected these accurately.
Uh-huh.
So how would you come up with 87% if your dangerous events were?
Yes, I mentioned that while I was talking. So I said this is only a slice of many events, but overall that is the mean of many confusion matrix. I only showed one of the slices that have a good one, but still the accuracy wasn't great as the confusion matrix here. But if you calculate the accuracy here, it won't be 87, it will be much better.
And how better is it?
I think that's almost a 90-something% for the confusion matrix as shown here.
So you did not really treat all of your 4,000 events of sleets.
I was only treating 3 days of events because I don't have much of data, and I need also to add some events to the model so it can learn on it.
Okay. And so then my question to you is, the 3 days of events enough to train a classifier to give you good accuracy?
Of course, it's not enough. If I want enough data, I would have like 3 years of snow events, and some models actually trained on 2020 and 2021, and some other models I can't because some features I didn't have back then, and I only trained my data on 2021, which have like like almost 8 to 11 days of hazard conditions. So I needed to only have a sample of 20% to 80%, so I can have a balanced model.
So you're saying that if we keep on collecting this data
Yes.
as year after year, this model should really give us a very
Yes,
accurate
as I said here, here, as I said, while adding data, it will drop, and GFS actually had a paper, like said, 100 years of performance, and they said by adding data, it will give you better results in the future.
Okay. Yeah, I don't have any more questions. Anybody else before we ask the committee to stand and the rest to leave? Alan, do you have any question for Afify?
No, very interesting though. Would like to get a copy of it so I can kind of study a little bit more and then continue our discussion on it.
Yeah. I'll talk with you about it, but the model that he showed in terms of classification of the head 12-hour ahead of prediction of hazardous is a very good model with the GFS that we use. But I sent you the presentation this morning, Alan. You should
okay. I haven't seen it yet.
Once I get the thesis, I think this thesis is complete too. So I'll send you the thesis too.
It's awesome.
Yeah, thank you for attending. Anybody else?
Very impressive. Very impressive. Thank you.
Anybody else? Okay, I would ask now everybody except the committee members to leave this Zoom session, if you don't mind. Thank you for attending again. I wish it was in person so we can have some food from Afify, but anyway.